Hello, dear students. Very good afternoon to one and all. Good afternoon, Madhukar Reddy. Good afternoon, Vedant. So before moving on to the class, I would like to launch a poll. Just let me know if I'm visible and audible to you guys or not. Vedant and Madhukar, can you able to see me? Okay. Good afternoon, Christina Priyadarshini. Okay, fine. Now let's go ahead with the class. So we are dealing with the haloalkanes and haloarenes, right? So in the previous class, we have discussed about the properties, right? Physical properties and some of the chemical properties of haloalkanes. So in the physical properties, we have studied that the haloalkanes are colorless and they are less soluble in water, and the boiling point of haloalkanes will be little bit higher than. Okay. Am I audible now? Is my voice clear? Yes. Okay. So the third point was the boiling point, right? The boiling point of haloalkanes and haloarenes, they are very, very high compared to the hydrocarbons of the same molecular mass. Okay. So this is all we have seen under the physical properties. So these are the very important physical properties I have told you. And coming to the chemical properties, there were three reactions, right? One is electrophilic substitution, and the second division is nucleophilic substitution, and the third reaction is reaction with metals. And among these three, we have started with the nucleophilic substitution, and there were two types. One is SN2 and the other one is SN1. And among these two types, we have discussed some points under SN2 reaction, right? So SN2 is a single step reaction, I told you, and it follows second order kinetics. Second order kinetics means the order of the reaction will be 2, right? And here if you see, there will be the formation of pentavalent transition state. So pentavalent transition state means there will be 5 bonds around the carbon, okay? The carbon which is bonded with the nucleophile. And coming to the configuration, in SN2, inversion of configuration takes place. Okay. And after completing the SN2, I have discussed some stereochemical aspects of SN2 reactions, right? So in the stereochemical aspects, what we have discussed? In the stereochemical aspect, I have discussed about the optical activity. This was the first stereochemical aspect. And we have taken an ordinary light. It was passed through the prism and it gave the plane polarized light. And if the compound is optically active, it will rotate it into two different directions. And if it is optically inactive, it won't rotate the plane polarized light at all, right? So this is what we have discussed in the previous class. Now, in today's session, we are going to see the second stereochemical aspect, which is called as asymmetry and chirality. Okay. So, shall we move ahead? Do you have any doubts so far? I hope everything is clear from the previous class topic. So, if you're getting any doubt, you can let me know. Okay. So, let me move into the asymmetry and chirality. So, let me take an object. Okay. Object means I'm going to take my hand. if I take the mirror image of this hand, I will get the hand like this, no? This is the mirror image of the hand or the object which I have taken. Okay. Now, I will take one more object. Let me take a conical flask. And if this conical flask, if I get the mirror image of this conical flask, I will get the same image like this. Now, what you do, take the object. First of all, take the first object. I mean the hand you take and try to place it over the mirror image. Okay. So now here the hand is non-superimposable. Right? The hand is non-superimposable. I can able to see the hand, the mirror image hand below the hand, below my hand, right? So it means that the object is non-superimposable. If it is non-superimposable, then it is called as an asymmetric object. Okay. So now I will take the second object, the conical flask I will take and I will try to place it over the mirror image. Now you see, can you able to see the second conical flask which is below the first one? Can you all able to see? Yes or no? Can you all able to see the conical flask, the mirror image of the conical flask from the front view? Yes or no, students? Is it superimposable or non-superimposable? Is it superimposable or non-superimposable? The second object. What do you guys say? Yeah, very good, Vedant. It is superimposable. Superimposable means we won't be able to see the object, the mirror image object, which is below the real object. Okay. Then it means the system is symmetric in nature. Okay. So what is meant by asymmetry? The image or the object should have the non-superimposable relationship. Got it? So this is about the asymmetric system. Okay. All the asymmetric molecules will have optical activity concept. All the asymmetric carbon or the asymmetric center containing molecules are optically active in nature. Okay. So now I will go ahead with the chirality. So for this I have taken a molecule. So in the center I have a carbon and it is bonded with 4 different atoms or groups and they are A, B, D and E. Okay. And C is the carbon. Got it? If a carbon is bonded with 4 different atoms or groups, then that particular carbon is a chiral carbon. It is a chiral carbon. What is meant by chiral carbon? A carbon which is attached with 4 different atoms or groups. Okay. So now what I will do, I will take the mirror image and I will get the image like this, right? So now what I have to do, I have to take the real molecule and I have to place it over the mirror image. So you just see here, if I place it over this, what I'm getting? Am I getting the superimposable relationship or non-superimposable relationship? Tell me, is it superimposable or non-superimposable? Yeah, very good. It is non-superimposable. So if it is non-superimposable, then what is the optical activity? It is optically active or inactive? If the system is having the non-superimposable relationship, then the molecule is optically active. Very good. Okay. Optically active. Very good, Shaheen and Vedant. Your answer is correct. So if a compound has to be optically active, then the criteria is it should have the non-superimposable relationship. Okay. So non-superimposable relationship means the system will have a chiral carbon or the asymmetric carbon. Chiral, asymmetry, both are same only. Okay, chiral carbon, asymmetric carbon, all of them are same only. Okay, so then we call the compound is optically active in nature. All right. So now we will go ahead with some examples of optically active compounds. So first I have taken one compound which is a lactic acid. Can you tell me whether this lactic acid is optically active or not? By looking into the carbon, can you tell me whether the lactic acid is optically active or not? Can anyone tell me whether the lactic acid is optically active compound or optically inactive compound or not? In the title itself, I gave you, right, the examples of optically active. Yeah. Why it is optically active? Why it is optically active? Very good, Madhukar. Shaheen, why it is optically active? Students, why you guys have said it is optically active? Yeah, because it is having asymmetric carbon or the chiral carbon, right? So which one is the chiral carbon? The center carbon is a chiral carbon because it is attached with four different groups. Four different groups. So the center carbon is a chiral carbon or asymmetric carbon. So the compound is optically active in nature. Okay. So now I will go for one more compound. Tartaric acid. Tell me whether tartaric acid is optically active or not. I will tell you it is an optically active compound. Okay, since the title itself says the examples of optically active compounds, tartaric acid is also an optically active compound. Now, you tell me how many chiral carbons are present in tartaric acid? How many chiral carbons or how many chiral center is present in tartaric acid? Only one? Only one? The correct answer is 2. Okay, you see here. Both the carbons are optically active. I mean, both of them are chiral carbon. Yes. Shaheen answer is good. Correct. So if I take the first carbon, this is one group and this is another group. And this is the third group. And this is the fourth group. Okay. So it is attached to the same type of groups. It is attached to the same type of group, but it is not having the superimposable relationship. Does not having the superimposable relationship. If I take the mirror image of this tartaric acid, I will get an object. I will get the mirror image of this compound. And if I try to place that over this, it will not get superimposed. Okay. So the two carbons which I have marked with the star are asymmetric carbons. Got it? There are two asymmetric centers here. So this is all about the asymmetry and chirality. Compound has to be optically active, then it should have non-superimposable mirror image relationship, or it should have a chiral center. Okay. So now we will go ahead with the third stereochemical aspect called retention, inversion, and racemization. Okay. Before moving on to this concept, tell me whether the molecule which I am showing with you on the screen is optically active or not. Tell me whether this compound is optically active or not. Is it optically active? Very good. Yes, because it is bonded with four different atoms, right? So it is optically active in nature. So now what I'm going to do, I'm going to take this compound and from this compound, I'm going to replace the X with the Y. So here I have X, right? I'm going to replace this X atom with the Y atom, some other groups or some other atom. If I replace, I will get the product like this. Okay. So this is called as compound A. This is called as compound A. And if some other Y group is replaced, or if some other nucleophile, I can say, if some other nucleophile is replacing this X, and if I get this kind of configuration, this compound is called as B. Okay. What is the difference between these two? Here, the new nucleophile Y which I have replaced is on the same direction of this X. X is also left, Y is also present in the left side. Okay. But in the compound B, if you see, X is on the left, but the Y is on the right. Y is on the right side of this carbon. Okay, Y is on the right side of this carbon. Now, I'm getting two compounds with the two different configuration. One compound is called as A and the other compound is called as B. If these two compounds are present in equal amount in a mixture, okay, if these two compounds are present in equal amount in the mixture, I mean the one with same spatial arrangement, which is called as retention product, and the other one with different spatial arrangement, which is called as inversion product, then both of them will be present in 50-50 amount. If they are in 50-50 amount, then the process is called as racemization. The process is called as racemization. All the racemization products are optically inactive in nature. They are optically inactive in nature. Okay, so what I have done, I have got two compounds, one with the same configuration of the reactant and the other one with the different configuration of the reactant. Okay, if I get the same configuration, then it is called as retention product. If I get the inverted configuration product, then it is called as inversion product. But both will be present in equal amount in the mixture. Okay, 50-50. So those mixture is called as racemic mixture and the process is called as racemization and the compounds will be optically inactive in nature. Is it clear to all of you? Do you have any doubts here in this retention, inversion and racemization concept? Stereochemical aspects means some thing which is related to the configuration. Okay. The placement of or the arrangement of atoms in a space. Got it? Students, do you have any doubts here? Shall I go ahead with the next reaction? So here I'm completing the stereochemical aspects of SN2 reaction. Okay, optical activity. Then the second one is asymmetry and chirality. Third is retention, inversion, and racemization. Okay. So do you have any doubts here? Say yes or no, students. Vedan, Shivamani, Jay Krishna, Shaheen. Yes. Fine. So here we are closing the SN2 part. Now the next reaction is the second type of nucleophilic substitution, which is called as SN1. Okay, the full form of SN1 is substitution nucleophilic unimolecular. And since the number 1 is present for this, it follows first order kinetics. The order of the reaction will be 1. Okay. So what is meant by 1? The rate of the reaction depends only on one reactant. The rate of the reaction depends upon only the substrate or only one of the reactant, which is called as haloalkanes. Okay. So in the nucleophilic substitution reaction, we will have two reactants, right? So one will be the substrate and the other one will be the nucleophile. And we will get a product, leaving the other nucleophile outside, okay, which is present in the substrate. So here, the rate of the reaction doesn't depend on both of these reactants. It will depend only on the substrate. Okay. And it follows two-step mechanism. It follows two-step mechanism. If you remember about the SN2 follows single step. Okay, SN2 reaction is a single step reaction. But SN1 reaction is a two-step reaction. Okay, I will show you those two steps here. Let me go with the mechanism so that you can understand it. I'll go with step 1. Step 1 is the formation of carbocation from the substrate. So how does a carbocation form from this substrate? So let me take the substrate. You see, a carbon is attached with the A, B, X and D. This is a substrate. And now in the first step, there will be the formation of carbocation. So it is formed by leaving the X, where X is the nucleophile. Okay, X is the nucleophile and X has left this compound and we are getting a carbocation from this reactant. Okay, and the hybridization of the carbocation is sp2. Okay, all the carbocations are sp2 hybridized system. So this information you might have studied in your 11th class. Okay, hybridization of carbocation is sp2. If the hybridization is sp2, the geometry will be planar. It is trigonal planar. It is looking like a trigonal planar structure, right? So if the hybridization is sp2, then the geometry will be planar. So initially the geometry is tetrahedral. Initially the geometry of the reaction, geometry of the reactant is tetrahedral. But once it forms the carbocation by leaving X minus, it is getting converted to planar structure. Okay, this is step number 1. And the step number 2 is the attack of nucleophile. So this is the carbocation. Okay, this is the carbocation which we got from step 1. Carbocation will have empty p orbital, which you can see in the green color. And since the geometry is trigonal planar, so all the atoms are lying on the same plane and the p orbital is perpendicular to the plane. Okay, so now to this carbocation, nucleophile is trying to form the bond. So let me add the nucleophile. Okay, so now the nucleophile can come from above as well as from below, right? As well as from below. Can you all able to understand? Can you all able to visualize this? Shall I show this again, students? So what I have said, we have a plane, trigonal plane, and all the atoms are located on the plane. Okay. Now, the p orbital is perpendicular to the plane. P orbital is perpendicular to the plane. So now what will happen? The nucleophile can come and form the bond with the carbocation from upward direction, okay, as well as from the downward direction. Got it? So both the products are possible. Both the cases are possible. If it comes and forms the bond from the upward direction, we will get a product like this. And if it tries to come from the other way around, we will get a product like this. Okay. So now what is this? So in one case, if you see the nucleophile is on the same direction with that of the reactant. In the reactant also we had the X atom, X nucleophile in the left side, right? So this is the retention product. And here in the other product, you see the nucleophile is present in the right side. Means this is the inversion product. This is the inversion product. Now, if we get two products in 50-50% amount, then the process is called as racemization. Okay, process is called as racemization. So what are the points we have studied under SN1? What are the points we have studied? We took a reactant or the substrate. Actually, it follows two steps. In the first step, X is leaving the reactant or the substrate and it is forming a carbocation with trigonal planar in geometry. And if the nucleophile is added to this, it forms two different products. Okay. So one product is the retention product and the other one is the inverted product. So this is the first step, which is called as formation of carbocation. And this is the second step, which is called as attack of nucleophile. So SN1 is a two-step mechanism. Okay. So here we have two reactants. One is the first molecule, the substrate molecule, and the other one is the nucleophile. But the rate of the reaction depends on the slowest step. The rate of the reaction depends only on the slowest step. So first step is the slow step and the second step is the fast step. Okay. So usually the slow step is called as the rate determining step. Okay. Slow step is called as the rate determining step. So the rate of the reaction in the rate determining step, if you see, there is only one reactant. So the rate of the reaction depends only on the one of the reactant, which is the substrate. Okay, or I can say the substrate is the alkyl halide. Substrate is the alkyl halide. So since the rate of the reaction depends only on the concentration of alkyl halide, it is called as SN1 mechanism. Okay, this is the formation of cation and this is the racemized product. Clear? And coming to the order of reactivity in case of SN1 is directly proportional to the stability of carbocation. So there are three carbocations. One is primary and the other one is secondary. Third one is tertiary. Among these three, tertiary carbocation is more stable. Okay. So since the tertiary carbocation is more stable, so the tertiary carbocation will be more reactive in nature. So if I write the reactivity order for primary, secondary and tertiary, it will be like this. Okay, it is just the opposite of SN2 reactivity order. Okay, in case of SN2, primary alkyl halide will be more reactive and in case of SN1, tertiary alkyl halide is more reactive in nature. Got it? So these are the points you have to keep in mind regarding SN1. So is this clear to all of you? Do you have any doubts from SN1? Shall we compare SN1 and SN2? Shall I compare and give you some points about SN1 and SN2? Do you have any doubts in SN1? Students? I'm waiting for your reply. Do you want me to explain anything? Do you have any doubts, students? Which one is more stable? That's what I told you. Tertiary alkyl halide will be more stable. Tertiary alkyl cation is more stable towards SN1. So the reactivity will be more for tertiary. Okay, Vedant? Is it clear? Okay. So now we will compare SN1 and SN2. Okay, SN1 versus SN2. So let me have it in a tabular format. So the first point is SN1 is a first order mechanism and SN2 is a second order mechanism. Order of the reaction is 1 and there it is 2. And SN1 is a two-step mechanism and here it is a single step mechanism. Okay. And here in SN1, carbocation intermediate is formed and in SN2, pentavalent transition state is formed. Okay. So here we are getting an intermediate and here we are getting a transition state. Got it? And in case of SN1, rearrangement is possible. The nucleophile can come from above as well as from below, right? So there will be the possibility of rearrangement, but in case of SN2, there is no such rearrangement because the nucleophile would have left the substrate one side and the new nucleophile will come and approach the carbon from the other side. So rearrangement is not possible. And the fifth point is the order of reactivity. In case of SN1, it depends on the stability of carbocation. Okay, it depends on the stability of carbocation, but where tertiary is more stable. And in case of SN2, it depends on the hindrance. What is hindrance? The steric hindrance. Steric hindrance means what is that? Crowdedness. Steric hindrance means crowdedness. Okay. If the crowd is very less, then that will be more reactive towards SN2. So in case of primary alkyl halide only, the crowd will be very less. I have already explained this to you in the previous class. So primary alkyl halides are more reactive towards SN2 mechanism. Got it? Is it clear to all of you? Shall we go for the second type of reaction under haloalkanes? We have three reactions, right? One is nucleophilic substitution. And now only I have completed the nucleophilic substitution. The second reaction is elimination reaction. Shall I go ahead with the elimination, students? Do you have any doubts in the substitution reaction? The nucleophilic substitution reaction? Okay, let me go ahead with the elimination reactions of haloalkanes. Okay, this is very easy. Elimination reaction of haloalkane is otherwise called as dehydrohalogenation. Dehydrohalogenation. D means removal. Okay, what I'm going to remove? I'm going to remove the hydrogen and one halogen. Okay, so elimination of HX is called as dehydrohalogenation reaction. So let me take the alkyl halide. This is the alkyl halide. Okay, so alkyl halide can be CH3, CH2X. Okay, now this alkyl halide has to be treated with alcoholic KOH. Has to be treated with alcoholic KOH. And I have to heat this. If I treat this with alcoholic KOH, the hydrogen and the halogen will get eliminated. Okay, and there will be the formation of double bond between the carbons. Okay, so it will lead to the formation of alkene. So here the halogens are chlorine, bromine, and iodine. It cannot be fluorine because fluorine is very, very small, right? So it cannot, the carbon fluorine bond cannot be broken down easily. So we will not use the fluorine over there. So in the halogens will be chlorine, bromine, and iodine. Got it? So this is called as elimination. We have eliminated the hydrogen and the halogen. Got it? Now the halogen attached carbon is called as alpha carbon. Halogen attached carbon is called as alpha carbon. And the next carbon, adjacent carbon is called as beta carbon. Okay. Since the beta hydrogen is getting removed, since the beta hydrogen is getting eliminated from the alkyl halide, this reaction is also called as beta elimination reaction. Okay. Beta elimination reaction. So there are two names. One is dehydrohalogenation and the other one is beta elimination reaction. Okay. So elimination will happen only if we use alcoholic KOH. Alcoholic KOH or alcoholic NaOH. You can use anything, but it should be alcoholic part. Okay. Now, what are the highlights of this elimination reaction? So, unlike substitution, nucleophilic substitution, In the elimination reaction, there is no carbocation formation during the reaction. Okay, we won't form any carbocation, we won't form any intermediate, so nothing is formed. And there is no rearrangement also, no rearrangement of the atoms also. And if you look into the order of the rate of the reaction of alkyl halide, so for elimination, tertiary alkyl halide is more reactive compared to secondary and primary. Okay, so like SN1 reaction, tertiary alkyl halide is more reactive towards elimination reaction. Got it? So this is the very important point. The last point is a very important point. You have to keep it. So if you take an tertiary alkyl halide and try to treat it with alcoholic KOH, immediately the hydrogen and halogen from the tertiary alkyl halide will go out and it will form the product. Okay? Is it clear to all of you? This is the elimination. I will give you one example to understand the elimination. Okay? So let me take a tertiary alkyl halide, CH3, CH3, CH3 and Br. Now this is treated with alcoholic KOH. And I'm going to heat this. What I will get from here? The halogen attached to carbon, bromine attached to carbon is alpha carbon. Okay. And the other carbons, the adjacent carbons are beta carbons. So here I have 3 adjacent carbons. So all the 3 of them are beta. So I will take 1 beta hydrogen. Okay, let me write CH3 like this. CH2 and X. So this hydrogen will go out and the bond will shift here and this carbon halogen bond will be broken down. So I will have CH3 and C. Here there is CH3 and there is a formation of double bond here. Here I will have CH2. The hydrogen and Br has gone out from the reaction. Okay, so here I am getting a double bond, right? So it is an alkene. So this is a tertiary alkyl halide. Got it? This is called as elimination reaction of haloarenes. Do you have any doubts from here, students? Is the elimination clear to all of you? This is very easy, very simple. Okay, and in one of the previous year, most of the years, the questions from elimination has come for both JEE and NEET. It's very easy and simple concept and important concept. Shall we go for the third type of reaction, which is called as reaction with metals? This is the last reaction. Reaction with metals is the last reaction of reactions of haloalkanes. Okay. So let me go ahead. The first reaction with metal is called as the preparation of Grignard reagent. Grignard reagent is RMGX. Okay. So this person is Grignard, Victor Grignard, and he got Nobel Prize in Chemistry for this reaction. So here, this person prepared the reagent with the help of alkyl halide. So he took an alkyl halide, RX, and he treated this with the magnesium metal. Okay, the metal is magnesium. In presence of dry ether, he got RMgX. So the magnesium is going and getting inserted between the R and X. So RMgX is called as alkyl magnesium halide, which is called as a Grignard reagent. Okay. So if I have CH3Cl, what I will get? What will be the product, students? In presence of magnesium and dry ether, I will get CH3 MgCl, methyl magnesium chloride. Okay, alkyl magnesium halide. So here it is called as methyl magnesium chloride, which is a Grignard reagent. That's all. So the reaction with magnesium metal is leading to the formation of Grignard reagent. Okay. Then the second metal is The second metal reaction is called as Woods reaction. And in Woods reaction, we have to take we will form the hydrocarbon from alkyl halide. Okay. So here the metal that is being used is sodium. Alkyl halides are treated with sodium metal in presence of dry ether to form the higher alkanes, which are called as hydrocarbons. So take Rx, which is the alkyl halide, and treat it with sodium metal. So 2 sodium you have to take, and 2 alkyl halide you have to take. So I have written the first alkyl halide here and the second alkyl halide here. Okay, in presence of dry ether and sodium metal, 2 NaX has to come out. Okay, if I take out the 2 NaX from the compound and if I combine both the R group, I will get the product like this, right? RR, with the removal of 2 NaX. And this is the alkane. RR is nothing but the alkane. I will give you an example, you see. So I have taken bromoethane. So this is bromoethane. So 2 moles of bromoethane is treated with 2 sodium in presence of dry ether. So now what I have to do? I have to remove the 2 NaBr. So remove the 2 NaBr and connect the 2 alkyl group. What I will get? C2H5 bond C2H5. Right? So totally we have 4 carbons here. So the 4 carbon containing alkane is called as butane. Okay. So we have formed the hydrocarbon butane here from this bromoethane. Got it? So I will take one more reactant, which is called as bromomethane. So in case of bromomethane, we have CH3Br, 2 moles of CH3Br. If it is treated with sodium, metal and dry ether, just remove the 2 NaBr from this and connect the 2 CH3. So here we have only 2 carbons. So it is called as ethane. It is called as ethane. So if I take 1 carbon containing haloalkane, I am getting the 2 carbon containing product. If I take 2 carbon containing haloalkane, I am ending up with 4 carbon containing alkane. Okay. So if I take 3 carbon containing haloalkane, I will end up with 6 carbon containing alkane. If I start with 4 carbon, I will end up with 8 carbon. So what do you understand from this? From the Woods reaction, only even number of carbon containing alkanes can be prepared. Okay. From the Woods reaction, which is the reaction with sodium metal, only the even number of carbon containing alkanes can be prepared. Got it? Odd number of carbon containing molecules cannot be prepared if I take the 2 moles of the same reactant. Got it? So it means only the symmetrical alkanes can be prepared using Woods reaction. Symmetrical means even number. Okay. Only the symmetrical alkanes can be prepared using Woods reaction. Got it? So do you have any doubt? So there are 2 reactions under the reactions of metals. One is with the magnesium metal and the other one is the sodium metal. Okay. So let me summarize. So today we have discussed some of the stereochemical aspects. Okay. And later on I have come to SN1 reaction. And I told it is the first order reaction which follows 2 steps. And it leads to the formation of carbocation and the racemization occurs. Okay, this is all about SN1. Then we have compared SN1 and SN2, right? Then once we complete the nucleophilic substitution, secondly, we have studied the elimination reaction in which we took an alkyl halide and treated that with alcoholic KOH and it led to the formation of alkene. And later on, the third reaction is reaction with metals. The first metal led to the preparation of a Grignard reagent. Okay. And the second is called as Woods reaction, where the alkane is formed from the alkyl halide. Okay. So these are the three reactions of haloalkanes, or I can say these are the three chemical properties of haloalkanes. So with this, we have completed the chemical properties of haloalkanes, and in the next class, we are about to discuss the chemical reactions of haloarenes and the polyhalogen compounds. Okay, so mostly I will try to finish this lesson in the next class. Okay, so do you have any doubts from today's session, from the elimination, from the SN1, or from the reaction with metals concept? Do you have any doubts, students? No doubt? If you have any doubt, you can put it in the chat box. If you don't have any doubt, I have launched a poll. You can give me your answers in the poll and you can get ready for your next class. Okay, thank you so much for attending. So from next class onwards, try to join on time. Okay, then only we can cover more concepts. Already we have only 1 hour in a day. So please try to join on time. Okay, try to avoid some technical issues and please join on time. Okay. Thank you so much to all of you. Thank you, Vedant. See you in the next class. Bye-bye. Take care. All of you, please give me your answers in the poll.